Welcome to this edition of Sharp Shorts. Today we're going to talk about chemical bonds. Now, as a chemistry student, if you want to help yourself be your best, there's two things really to master. Number one is mole calculations, which we worked on earlier this year. The second thing will be balancing chemical equations, which is difficult to do if you are unable to write chemical formula. And that's why we start with chemical bonds and discuss how to write different chemical compounds. Once you get that language down, writing the equations becomes much easier. Now, we're not going to talk specifically about the bonds in past courses. I'm sure you've been told there's two different types of chemical bonds, ionic and covalent. In all reality, what I want to show you here for general background is chemical bond is just one thing. Okay? You have, in some way, shape, or form, you have an attraction between the positive nucleus of one particle, one element, with the valence electrons of another. Okay? And vice versa over here. Okay? It's that overlapping, that working with the valence electrons, that interaction that holds them together. Now, how they do that, whether that's ionic or covalent, the properties that it brings that, and how those compounds and species interact, then that is why they separate the two. And it comes down to, as we'll talk about in a later film, difference in electronegativity. But just to get the understanding that chemical bond is just one interaction between the elements, and really it's one type of thing. The properties allow us to classify them slightly different based on properties. Now today we're going to talk about ionic compounds and start you with binary ionic compounds as far as naming. Now, ionic compounds are formed, essentially, we'll talk about that in a minute, between cations and anions. When compounds ionize, and in their electrostatic charge of a positive cation and a negative anion hold them together. And that gives them different properties, like forming crystals. Generally, they're crystalline at room temperature. They have high melting points. They like to conduct electricity. Most of the ionic compounds we work with are a metal with a nonmetal. So I put the periodic table up here to highlight again that most of the periodic table is metals. You have that little metalloid area in there, and here's our nonmetals. Hydrogen over here is really a nonmetal insulating gas, but it is kept over here above the earth metal area just because of its electron configuration and the fact that it can have a +1 cation. Okay. All right. So here's a good example of ionic compounds. What you have probably been told in the past in the ionic bond is that you get a complete transfer of electrons. So here you have sodium. And we're going to make one ionic compound is table salt, sodium chloride. From what we know, from looking at the periodic table and stuff in electron configurations, is that sodium has one valence electron out here in its valence shell. And it would, preferably because of electronegativity and ionization energy and everything else, preferably it would rather get rid of that one electron, and then that would give it a neon type noble gas configuration, which would make it a much more stable in its octet. Chlorine, on the other hand, has 7 valence electrons in its outer shell. High electronegativity and high ionization energy. It would like to pick up, if it could, an electron and fill out its octet, and then basically take the same noble gas configuration as argon and make it stable. And so we will. And this is where they talk about the transfer of putting one to the other. And then what you have then is you have the positive sodium cation, you have the negative chlorine anion, you get some attraction between the positive nucleus, the valence electrons, the positive nucleus, the valence electrons, and you can form, and here's the formation of crystalline structure, but you can get that electrostatic charge there that creates that bond. And of course, with that, and the reason they're crystals at room temperatures is then you can get some intermolecular bonding in between to hold that crystal together. which we'll talk about at a later date. Here we go. Here's the types of ionic compounds we are going to talk about and figure out how to name. Binary compounds have 2 elements. Ternary or polyatomic have 3 or more elements. We'll talk about the transition metals, those crazy things in the D block, and scattered down into the higher levels of the P block that can have more than one charge. They can be both binary or polyatomic. And then we'll finish up with acids and bases. Again, ionic naming is driven by the number of elements and the cation. All ionic compounds are written cation first, the positive charge, and anion second. Okay. And let's just solidify that with a couple of great pictures. Cations are positive, and anions are negative, but they aren't just as negative as they are understood. But that makes an ionic compound. Okay. When ionic compounds, when they're binary, when they only have 2 elements, you take the anion ending and you change it to IDE. So for sodium and chlorine, that became sodium chloride. It's quite a simple way to look at things, and as we go through each of these different types of ionic and then covalent compounds, looking at them individually is the easier portion of it. It is when you have all those different types of ionic compounds and covalent compounds all jumbled together that you have to start looking for tricks that allow you to identify, is it a binary ionic, is it a polyatomic, is it an acid or a base, is it a covalent compound. And that's why we want to give you some background and tell you that a lot of times you're looking at a metal and a nonmetal with ionic compounds. Anyhow, naming chemical compounds, the nomenclature piece is easiest just by working on it, so I have some examples here, and there we go. We looked at that. 2 elements, sodium and chlorine. Here's 2 elements, magnesium and phosphorus. And this is what denotes them as binary ionic. They have 2 elements only. Even here in the named portion, strontium, bromide, aluminum, sulfide. Now, you may be asking yourself in this formula, which we'll get to when we work on these, is what are these subscripts 3 and 2? One thing important to understand is while ionic compounds are held together because of the attraction of a positive and negative, a cation and an anion, and we understand opposites attract, just ask my wife. While that holds it together, ionic compounds are neutral. So when you're writing the formula, you have to understand you must include enough of each, cation and anion, to neutralize the charge, and that's at the lowest possible level. Anyhow, back to here. When I'm writing these things out in word form, it's very simple. I look at the cation, I look it up on the periodic table, that's sodium. Don't mind my pen writing. And I write that down just as it comes on the periodic table. Oops. And then the next, the anion is chlorine, but I change all endings to IDE for binary ionic compounds. Okay. So it isn't sodium chlorine, it's sodium chloride. And that's one of those things that helps you define later on when I'm trying to understand how to name these things and how to separate binary from ternary and acids and transition metals and covalent compounds is that IDE ending. That does allow you to understand that oftentimes most of the time that's a binary compound and the anion is an element on the periodic table. Here we go again. I look up Mg, and that's magnesium. Pardon my writing as I get used to using this pen again. Okay. And I just write it as it is. My second element then is phosphorus, and that's a nonmetal on that anionic side of the periodic table. And so it's phosphorus, so I'm going to change and make sure it has an ID ending. Now, a lot of students will say phosphoride or things along that line. That's fine. We will get used to mistakes of saying phosphoride, oxygenide, nitrogenide, and everything else. There's not necessarily a set rule. I like to tell students that what you're looking for is some smooth, probably only two-syllable type deal. And that's why this actually becomes magnesium phosphide. Okay. So that's it. If I want to read the formula and write its name, then all I do is write down the cation as it is on the periodic table, and then take the anion and change the ending to ID. Again, this is the key component. Okay, and write the anion with an ID ending, and that will name them. Okay. Now, let's reverse this. Here we have the words written out. How do I write the formulas? Well, it's pretty much the same thing. I know it's just two elements, and I can go to the periodic table and I can look up the symbol for strontium as Sr. It's written first, so we'll figure out the cation charge in a minute, but you know that it's going to be positive. So if you struggle with your valence electrons and you're calculating ion charges, that will help you. And then I also, bromide means bromine, so I also write its formula, its symbols, and that's going to be my anion because it's written second. Now I have to go to my periodic table and I have to look and look at my how many valence electrons are there and where it's situated. And as I look at strontium, it's in the second column there with two valence electrons. It's going to be a whole lot easier to get rid of those two electrons and drop down and have my octet stabilized below. So that's going to be a +2. Bromine is in the same column as chlorine and fluorine and the other halogens. It has 7 valence electrons. It wants to pick up an electron. So it'll pick up one extra electron and fill out its shell. Now you see where the subscripts come in, because you have to balance these charges out in the lowest possible ratio. And all compounds are neutral. So what that means is, for every 1 strontium, I'm going to need 2 bromines, each one bonded to that strontium, each one have an electrostatic charge to that strontium. And so I write that as a subscript. And there is a formula for strontium bromide. It's a +2. 2 minus 1 is equals 0. I do not have to write the 1 subscript for anything. It's just assumed. And there's my chemical compound. Okay. Again, here's aluminum. I look on the periodic table. It's Al. I know it's first. It's the cation, so it's going to be positive, and I'll figure out its charge in a minute. Sulfide is sulfur, and it's going to be my cation. Okay. Now when I go look at aluminum, in the same column as boron and stuff, it has 3 valence electrons. It will want to dump those 3 and get to a stable octet from its filled shell below. Sulfur is in the same column as oxygen and that crew, and it has 6 valence electrons. So it would like to pick up 2 electrons and be a -2 charge. Okay. Now again, all compounds have to be neutral, and so I have to find some common factor, some common multiple of this at its lowest possible ratio that will show me how many of these cations and anions have to interact. And for 3 and 2, that lowest possibility is 6. And so in order to get to a +6 charge and cancel out, I'm going to need 2 aluminums, and I'm going to need 3 sulfur. And there's the formula for aluminum sulfide. Now, one way to think about it here with ionic compounds that you can look at is really what you do when the charge is not the same is essentially you're flip-flopping the charge with the subscript down below. Little subtle hint to help you. Okay. Anyhow, that's binary ionic compounds, and you should go practice the quiz, and our next video will be on ternary or polyatomic compounds.